Okay, let's take a look at these example problems together. Hopefully you've tried them a little bit on your own first, so that you can see whether you can do it or not, or what problems you're having, but we're going to go through them together. I might not do every last calculation, but at least get you set up with them. So let's look at the first one. It says, what is the strength of the gravitational force between the Earth and the Moon? So anytime you hear a question asking about gravitational force, it means we're going to use this equation since it's got an F in it for force. So I'm going to start just by writing that equation. So I have it here, F equals G, the gravitational constant, times the mass of the big thing times the mass of the little thing, divided by the distance between them squared. Now in this case we're dealing with the Earth and the Moon. Now you might be like, well, how can I possibly solve this? It doesn't give me any of the numbers, right? Well, we can look those up, right? What I need is the mass of the Earth, the mass of the Moon, and the distance between them. So let's see if we can find those, and I'll show you kind of a nifty way that we can find those. Those are in your book, at least somewhere, but we can look them up with Google. Mass of the Earth, mass of the Moon, and distance. And there's a neat way we can look them up. I'm going to switch to Google here. And I believe that if we just type in mass of the Earth, yeah, there we go. It tells us exactly what it is without having to search any web pages. So mass of the Earth is 5.97 times 10 to the 24. So let's put that in here. Mass of the Earth, 5.97 times 10 to the 24 kilograms. That's the units we want. Okay, and then we can do the same thing, hopefully, for the mass of the Moon. Let's try. There we go, 7.36 times 10 to the 22. So here we go, 7.36 times 10 to the 22. Okay, and so if we remember scientific notation here, we can tell that these are roughly 2 factors of 10 off, so roughly a factor of 100. The Moon is maybe 100 times less massive than the Earth. Now we also need the distance between them. Let's see if Google can give that to us. Distance from Earth to Moon. There you go. Best guess for the Moon distance from the Earth is 238,000, but we want that in kilometers, right? So I'm going to say in kilometers. Oh, it looks like it can't do it, but Wikipedia's got it there for us. Distance between the Moon and the Earth varies roughly in here. Oh boy, it's getting trickier, isn't it? So let's look at Wikipedia. Too much information. Here we can see on the right hand side the semi-major axis is 384,000 kilometers. Alright, now again you could look this up in the book if you want to, but we'll take it. We'll assume Wikipedia's got it right. So 384,000 kilometers. So I'm going to write that in scientific notation, 3.84 times 10 to the 5, right? Kilometers. Because I'm going to move that 1, 2, 3, 4, 5. Yep. Okay, so now I've got all these big numbers in scientific notation, and I have the gravitational constant. It's a matter of putting all of these things together into this equation. Now that might be a little tricky to actually type that into your calculator if you haven't done that with scientific notation in a while. So I just want to highlight something that you might have, a feature you may have on your calculators, which is this double E button. When you see the double E button, that button means times 10 to the. Times 10 to the power of. So if you wanted to say type in this mass 5.97 on your calculator, you would type 5.97 and then you would hit this double E button, E, and then you could just type 24. So it's already doing the times 10 to the for you. Alright, so practice doing this if you haven't done this in a while. You should end up with an answer, a force, that is, at least roughly, or pretty close here, to 1.97 times 10 to the 20 newtons. Alright? Let's take a look at the next example here. This is a little different because we aren't necessarily using numbers again here. It says the distance between two bodies is cut in half. What would happen to the force of gravity? So again, I see the word force, I know what equation I'm going to use, between the two bodies. Okay, so this is a problem where it's not giving us what these bodies are. We don't know if it's the Earth or the Moon or the Sun. All it's doing is telling us how much it changes, that it's cut in half. So this is another example of a ratio problem. We did a ratio problem when we were looking at small angle formula. And ratio problems are problems where something is changing by some factor. Something is doubled, or it's cut in half, or something like that. So let's look at this in light of the fact that this will be a ratio problem. Whenever we have a ratio problem, what that means is that the unchanged variables, variables that don't change, they will turn into just the number 1. Because if we're taking ratios and a number doesn't change, that number over itself would just equal 1. So in this case, we can sort of rewrite this equation. We're trying to find how much the force changes in this ratio problem. But when we rewrite the equation, we can replace something that doesn't change with the number 1. So g is the gravitational constant. It's a constant, it doesn't change, so we could replace that with the number 1. Now big M is the mass of one of the bodies. In this problem, it doesn't say anything about the mass changing, it just says the distance changes. So we're going to assume those masses are the same. So the big mass is the same, and the little mass is the same. So we have a lot of 1s. This makes it really easy. Now the distance does change. And so if something does change, what we do is we replace it with the fraction that represents how much it changed by. Right? So if something doubled, we would replace it with a 2. But in this case, the distance is cut in half. So we're going to replace it with a half. Now the really important piece here is that this thing is still squared. And any exponents we have to keep. We don't lose any exponents. So this is an important thing about ratio problems. We keep all exponents. Alright, and this will allow us to figure out how much the force changed. We have 1 times 1 times 1. So all of this whole thing is just going to tell us that the force, how much it's going to change, will be 1 over 1/2 squared. Well, 1/2 squared is 1/4. So this is 1 over 1/4. And this is kind of tricky. We don't often see this, a fraction over a fraction. But you can either type this into your calculator if you want to, or you could remember that when we have 1 over something, 1 over a fraction, it's like the inverse. And so this becomes just 4 over 1. So if the distance between the two bodies is cut in half, they're brought together closer. That means the force is going to be 4 times bigger. 4 times bigger. Okay, so it's kind of tricky. These ratio problems will pop up from time to time. Okay, both of those were using Newton's law of gravity. Let's look at a different kind of problem. This one talks about a hypothetical planet that orbits a distant star, and it has an orbital period of 3 years and an orbital distance of 2 AU. If you ever see a problem that's going to have AU in it, like astronomical units, that's the distance, okay, that's going to be a problem where we're going to be using this Kepler's third law revised here, this equation. Okay, so I'm going to rewrite that equation down here so that I have it. What that equation tells me is that the orbital period squared equals 4 times pi squared, right? Let's double check. 4 pi squared, yep. There we go. 4 pi squared times a cubed over, again, the gravitational constant, times m plus a little m. So big M plus little m. Now there's a little trick to this problem. It says this hypothetical planet orbits a distant star with an orbital period, okay, so capital P must equal 3 years, and an orbital distance of 2 AU. So, okay, here's my semi-major axis. Orbital distance would be 2 AU. Okay. Now, what's especially tricky about this is that we have this g here and this 4 pi. And it poses this issue of what units are we using. We have a period in years and a distance in astronomical units. But g is this crazy number which has units that are crazy too. The units aren't included here, but it wants things in kilograms and seconds, and we have to worry about units. So what we often do is we can rewrite this in a way that's a little less troublesome and allows us to use better units. If we're using units of our solar system, and stick with me here because it'll make sense in just a second. If we're using units in our solar system, then the equation can be simplified. And let me explain that real quick with what I mean here. If the period is measured in years, which if you think about it, is like a unit specific to the Earth, right? I mean, because a year is the time it takes Earth to go around once. And A is specific to the Earth as well. If A is in AUs, right, astronomical units is the distance between the Earth to the Sun, then this simplified equation works so long as our masses are expressed in a specific unit, which would be represented here, solar masses, m with a little dot in it, right? And this means basically one solar mass, the mass of our sun. So what's nice about this is if we're doing problems that are in years and astronomical units, we can use this simpler version of the equation, and then our answer, the mass, will be in units of solar masses, which is exactly what we want, because we want to know how does the mass of the star compare to the mass of the sun. And so we want to know the mass of this fictional star in solar masses. So let's now use this simpler version of the equation here with these numbers. So we're going to have p squared. Oh, and there's another trick we have to do here. See, this is a tricky problem. Okay, we have m plus m. Now, there's two masses here. And we have P and we have A, but we want to solve for the mass. So what do? We have the mass of the star and the mass of the planet. Well, this is another simplification that we often make, is if you have this enormous star, I mean just huge, and you have this tiny little planet, right? This planet probably has a mass that's, a millionth of the star. I mean, just incredibly small compared to the star. So if you have this enormous thing for big M and this tiny little thing for little m, adding that tiny little thing really doesn't make any difference. It really doesn't. I mean, what if you have a million and then you add 1? I mean, a million and 1 is basically the same as a million. So what we can do is we can simplify this even more. So even though we made it more complicated, if we're using the right units, Kepler's third law gets simplified again. And so long as we're using our solar system units, it works out this simple. So now I'm going to rearrange this equation to solve for mass, because that's what I'm interested in this case. So I multiply both sides by mass, and then I'll divide both sides by this p squared, and I'll end up with that the mass is equal to a cubed over p squared. So really this is probably the equation we should use most often, because most often we're going to be dealing with units of years and AU and solar masses. So now let's do this. The mass then is going to be equal to a cubed, so this is 2 cubed, over p squared, so 3 squared. And 2 cubed is 8, and 3 squared is 6. So this solar mass, let's see here, would be 4 over 3. So it would be roughly 1.3 solar masses. So the question asks us to compare the mass to that of the sun. Well, it would be 1.3 times the mass of the sun. Alright, so we did a lot of different math here. We found a simpler still version of Kepler's third law, which still has gravity built into it. And we've seen how we can use these problems to solve both ratio problems and problems where we actually have numbers to sort of plug in.